I'm Isabel Allen, Editor of Architecture Today. Welcome to this AT CPD webinar, Designing and Specifying Glass Rainscreen Facades, in partnership with Sto. I'm joined today by three colleagues. First of all, we have Jason Sayer. He's from Architecture Today, and Jason's going to be moderating the questions throughout the day. We've then got two experts from Sto, Darren Greenwell and Greg Astill. So I'm going to let Darren and Greg introduce themselves. Darren, can you tell us, please, a little bit about your role at Sto?
So my name's Darren Greenwell. I've been working for Sto for 3 years now. I'm the business development manager for the company. Work nationally, covering our glass and rain screen systems. Basically, that entails locating, identifying and generating opportunities for the system to be used nationally, and then providing a cradle-to-grave service to architects, principal contractors and subcontractors throughout the design and installation process to fruition.
Thank you very much. And Greg, can you tell us a bit about your role?
I'm Head of Product Management at Sto in the UK. Been in this role on and off for about 10 years now, and I manage a team that are responsible for the development, the adoption and life cycle support of all the facade and acoustic products and systems that we offer in the UK. So I ensure that the products that we bring to market are suitable for the UK market in terms of sales and their appeal. And also drive the compliance of those systems and products with UK building regulations and other regulations that we have in place within the UK.
Thank you. So both Darren and Greg are going to be on hand throughout this CPD to answer your questions. The CPD is divided into two parts. We've got session one is on design possibilities and specification. There'll then be a Q&A. Session two goes much more into detail about performance and compliance. Please enter your questions as they occur to you using the button on your screen. So now I'm going to introduce part one.
Welcome to this Sto Glass Rainscreen CPD video, which is in two parts. In this, part one, we cover rainscreen principles, the difference between a glass rainscreen cladding system and curtain walling, and the cladding material that can be used for a rainscreen system. The system benefits, colours and finishes will also be presented in depth to help you when designing a glass rainscreen system. Part 2 explores performance and approvals, including moisture protection, wind loads, impact and blast performance, and fire safety. In 1954, Fritz Stottmeister, the founder of the Sto Group, discovered a newspaper advertisement looking for a licensee for a new type of organically bound plaster, and convinced his father to invest. The new material quickly became a success, and the Sto brand was born, including the iconic yellow bucket. 2 years later, the company launched Stotherm Classic, and with it the story of facade insulation, which soon developed into Sto's core business field. Sto grew from a regional plaster and paint manufacturer to a leading international group of companies. Today, the group has 50 subsidiaries in 38 countries and employs over 5,700 people. Our business is known first and foremost for our cement-free plaster render finishes and reinforcement, which, when used as part of our external wall insulation systems, EWIS, and rainscreen cladding systems, offer a huge choice of attractive, durable, energy-saving, and hence cost-effective options for refurbishment or new build construction. In addition to our comprehensive range of facade renders and intelligent technology paints, we also offer a portfolio of sound-absorbing acoustic systems, solutions for concrete restoration, and interior coatings. Let's start with a brief history on rainscreen cladding systems. The technology comes from Norwegian farmers. They realized that cladding their barns with wood and leaving a ventilated cavity meant they could stop moisture damage. This is why rainscreen cladding was originally referred to as the open-jointed barn technique. It wasn't until the 1940s that the results of the Scandinavian investigations using timber cladding were incredibly positive, Rainscreen cladding being recognised as vastly superior to other building methods of the time, a fact that still largely holds true today. One of the most publicised examples of an early Rainscreen cladding project was the Alcoa building in Pittsburgh, US. Built in 1952, the 30-story building was clad in open-jointed aluminium baffles. It wasn't until much later, around the 1970s, that Rainscreen cladding became a popular building method. What is a Rainscreen cladding system? Rainscreen is a form of double-wall construction, and the outer layer keeps most of the rain out. A drained and ventilated cavity eliminates the remainder of the moisture by natural drainage and evaporation. The cavity creates a natural chimney effect, pulling the air through from bottom to top. The inner leaf provides thermal insulation, prevents excessive air leakage, and carries the wind load. Some systems may be designed with pressure equalization, whereby the positive air pressure in the cavity prevents water blowing into the joints. These systems are fairly rare, and a limited form of this effect may also be experienced with drained and vented systems, albeit not intentionally designed in. There are two main types of non-structural architectural glass systems: curtain walling and rain screens. Curtain walling is completely sealed against the weather. Rainscreen cladding has open-jointed panels and a ventilated cavity and is mounted on a substrate that provides the primary defense against weather ingress. In this CPD video, we're covering glass rain screens. Here's an example of a build-up of a typical Rainscreen cladding system. The substrate, which can be solid or sheathed steel frame. Then the mineral fibre Rainscreen slab insulation, thickness to suit U value, is fixed to the substrate with dowels. A subconstruction is then fixed to the insulation, which comprises stainless steel wall brackets, aluminium vertical and horizontal profiles, and fixings to suit the substrate. The outer leaf glass panel is typically 6 mm thick toughened glass bonded to a backing board. Thicker glass is available for applications where the panels are particularly large. Some glass Rainscreen cladding systems require clips or through fixings to resist wind loadings. The panel consists of three elements. The outer layer is a 6 or 8 mm heat-soak tested safety glass that is coated on the rear face with a mineralic pigment. The glass thickness is related to the size of the panel. The pigment is applied during the toughening process and baked into the rear surface of the glass. This means it can't be scratched off and will not fade. The safety glass is incredibly tough. Given sufficient impact, it shatters into small, safe chunks, not sharp shards, and remains bonded to the backer panel. The adhesive layer bonds the glass strongly and safely to the backer panel. It ensures the glass remains bonded and in place, even in the event that it is smashed. The backer panel is manufactured from perlite and forms a strong and stable platform for the glass. It is very dimensionally stable, not expanding, contracting, or warping under heat, cold, or moisture. The backer panel also forms a stable background for the horizontal carrying profiles that are screwed through onto the rear face. Glass panel sizes start at a base of 2.6 by 1.25 meters, and this is the most economical size. The largest panel size in terms of area is 2.6 by 2.5 meters. For horizontal format, the largest format is 1.5 by 3.75 meters. 8 mm glass is used for lengths over 2.8 meters. For vertical formats, the largest size is 3.75 by 1.5 meters, which can increase to 4.5 by 1.25 meters. Again, 8 mm glass is used for heights over 2.8 meters. Smallest formats are 175 by 250 mm horizontally and 250 by 100 mm vertically. Also, non-rectangular shapes are possible, as well as curves and arcs. Glass is not only a remarkable material in terms of appearance, but also its design flexibility. You can choose single color, multicolour or metallics for your bespoke design, with a variety of finishes available. Textured glass is also available, adding a three-dimensional element to the surface. Glass Rainscreen panels are generally coloured. It is important to choose a system where the colours are fused to the back of the glass and applied before the toughening process. The coloured enamel melts into the glass at over 600 degrees Celsius. This enamel is colour-fast and permanent. Avoid painted glass, as this may not be as durable. The colour system typically used is RAL, standard colours. There is flexibility to produce panels to manufacturers' colour ranges. It is also possible to use multiple colours within the same panel. Traditional standard float glass carries a greenish hue from the natural levels of iron oxide in the glass. It is possible to have colourless toughened glass. This is called OptiWhite. By using the OptiWhite colours, the panel will lose the green hue and reflect the true colour applied to the rear of the glass. Screen printing and digital printing offers additional design possibilities. The graphic is fused to the back of the glass and bonded to stop peeling or wear during the enamelling process. Patterns, illustrations, photographs, or corporate logos can be designed for the glass panels. The finish of the glass surface can also be varied. Specialist matte finishes are available and tend to carry a surcharge over standard gloss finishes. There are also ranges of mirrored and metallic finishes available with toughened glass panels. Let's look at the different types of finishes that are available for glass panels, showing the textured, digitally printed, mirrored, glossy and matte options. A huge range of textures are available from different glass manufacturers, and many are suitable for use on glass Rainscreen systems. Having a bespoke panelized cladding system allows the designer to control the visual interpretation of the building grid. Typically, joints between panels are between 5 and 12 mm. Almost any shape is practically possible to develop. Joints and recesses can be reflected as a design element. Panels must be shaped prior to the toughening process. The surface level of the cladding can also be controlled by using the wide range of bracket sizes that are available. That concludes part 1 of this Sto CPD video. In part 2, we'll cover glass Rainscreen performance, including moisture protection, wind loads, impact and blast performance, and fire safety.
Jason Sayer has been having a look at the questions as they come. So Jason, what's been coming up?
So the first one is, what sizes and shapes of glass panel are available?
Darren, I'm going to put that question to you. We did touch on it, but what are the standard shapes and sizes, and then what's the potential for deviating from those?
Okay, so standard sizes for glass. I mean, the most economical size is obviously the size of the backer board, so a 2.6 by 1.25. But primarily, we're governed by the length of the rail that goes on the back of the board, which is a 3 meter length rail. So in theory, you can have just over a 3 by 3 meter square piece of glass, so 9 square meters in total. But you can go, if you're going in portrait style, you can go over 4 meters. But you can also have, you're not governed by squares, you can have rectangles, triangles, circular shapes. It really is down to whatever the aesthetic is, but we're able to achieve all of those within the parameters of those sizes.
But presumably there's a point where the cost just becomes prohibitive if you're going for too complicated shapes and unusual sizes.
Yeah, absolutely. I mean, we get asked to do a number of things by architects, and obviously what we do is we go away, we provide estimates based on what they're trying to achieve, and then we go back to the architects and say, okay, so what you want to achieve is in this ballpark. At which point the architect can go back to the client and either say yes or can have a sort of redesign and a rethink about what they want to achieve, and perhaps be a bit flexible in how they go about achieving that. I mean, in one instance, we had an architect who wanted lots and lots of triangles, which in practical terms, when you're using an open joint system, makes it difficult. So what we did instead was we printed the pattern on rectangular glass to achieve the same aesthetic. So the cost saving was significant. So again, it's always good to talk to us about options on sizes, patterns, colours, that sort of thing.
So I guess it's all about talking early in the process, isn't it? So you can actually really think creatively about the best solution.
Yeah, absolutely. Early engagement, keep the lines of communication open. And because it's a system that's been going a number of years now globally, we're able to draw on the experience of the Sto Global Group. And there are things that have been done around the world that may not have been done in England. So there's nothing new under the sun, so to speak. So often we're asked to do things and we can refer back to our colleagues elsewhere and that they can advise, yeah, this is how we did it.
We actually have one more in relation to panel sizes, and one audience member is curious about the thickness of the panel in relation to the size of it, which you alluded to in that presentation. They were wondering if there were any ratios, in relation to that kind of thickness ratio in relation to the size of the panel, and if you have any examples of that.
Up to the panel typically uses the only variation really is 6mm or 8mm glass, and then we have around 2mm of adhesive and a backer panel onto that. So the total depth of the panel is 22mm with that build up. When you go beyond a certain size, so typically above 2.6 by 1.25, then we use a thicker glass, an 8mm glass, to cope with the first of all, we have jointed panels behind to cope with the joints, and also for the larger format. So then you would increase the thickness by just 2mm. So really quite slim panels themselves. And behind that, you have typically you'll have a carrier rail, which is about 20-25 millimeters deep. And then that's hung on to brackets which can accommodate insulation. So the insulation then is done to suit the U values that are required. So yeah, quite a thin panel, but also pretty strong with the toughened glass that we use.
Actually, I'm glad you mentioned adhesive there, because you actually have one just come in about that, I think, responding to what you said. There are two actually on that, so I'll combine them. The first is, how is the adhesive layer applied? Is this pre-made or done on site? And if the latter, how is it done? And is a particular adhesive used, and is a specialist required? And the one that came in, as you mentioned, that was, is more adhesive used for the thicker glass? Because you mentioned 2mm layer of adhesive, but is more required for the heavier 8mm glass?
So the adhesive is laid on in a pre-designed pattern, and that's done in the factory. So the glass sheet is bonded to the backer panel in the factory. It arrives on site also with the rails on the back prefixed. So all that's needed to do on site is to hang it onto a substructure. And yeah, with regard to the thickness of adhesive, no, that doesn't change with the thickness, with the glass thickness. That remains the same, irrespective of which thickness of glass that we use. So yeah, I think I've covered all the points there.
Jason, let's go back to you. Did that cover all the points? I slightly lost track.
So the question about more adhesive being required for the thickness of glass, yes. And again, the other point was about, is a specific adhesive required?
Yes, there is a specific adhesive. A specific adhesive required that we use, that we use for in all of the testing. So it has to be the same adhesive that we use with all of the testing that we've done in the background. So it is a certain one, but obviously that's part of our IP. So we don't really release that.
One audience member asks, is it possible to see a sample for screen printing in a detailed pattern?
Oh, Darren, let's go back to you for that. So what's your position on doing samples to look at?
Yeah, absolutely. I mean, our standard sample size is a 300 by 200 mil sample size. So it's sort of A4 sized. We're able to do larger, but then there's a cost element that comes attached to that. Screen printing itself can be quite expensive, depending on, once you've done the sample, if the area that you're covering is going to be significantly large. So So with screen printing, it's all about the cost of the setup of the individual screens themselves. And obviously you can use a screen perhaps 50 times, but then you have to create another screen and another screen in order to keep replicating. So depending on the size and scale of the project, sometimes screen printing isn't the best option. Sometimes it's digital printing, particularly where you've got a non-repetitive pattern or you've got individual shapes, icons, logos, signage, that sort of thing that can all be digitally printed and then back enameled onto the glass before it's baked. So once it's baked, that's it. The logos are on the back. But yeah, we're able to provide samples. So again, if the person asking the question wants to get in touch with us afterwards and detail some of the specifics that they're looking for, I can advise whether screen or digital printing would be the best option, and then move that forward with them from there.
And have you got any examples, Darren, of instances where you think the screen printing has worked particularly well for people to look at?
Yeah, absolutely. Quite topical, actually, is the Elizabeth line that was opened by the Queen a couple of months ago. And over on the eastbound Elizabeth line on the wall, concourse wall at Paddington Station, there's a significant area of Sto Ltd glass there, which has got an interlocking circular pattern. So circles within circles that then interlock with adjacent circles. So the actual setting out of the panels in order to achieve that was quite onerous, but the overall effect achieved is very, very good. We're currently I was just going to say that we're currently in discussions with a client in Manchester for a very, very intricate pattern, which we're opting to go digital print, and they're currently looking at all the options on that as we speak.
Oh, well, that kind of answers my question. I was going to say, if you take that example, which probably a lot of people can actually picture, why did you go for screen printing rather than digital? Is it because of the kind of crispness and simplicity of the design?
Yeah, absolutely. Yeah, screen printing gives a nice crisper edge to the finish over and above digital printing, which is obviously pixelated. So from that aspect, it was good, and basically the reuse of the screens and the sort of area coverage, screen printing certainly was the preferred option for that project.
And is there much of a cost difference between screen printing and digital printing at that kind of scale?
If it depending on the size of the project, because with obviously digital printing, you haven't got to worry about screens and the cost of setting up individual screens for reuse. So you'll probably find that digital printing is slightly more cost effective than screen printing, but again, it's economies of scale, isn't it? So if you've got large areas and you're looking at digital printing, then perhaps screen printing is the better option. But then if you're looking at smaller areas and keeping costs down by not using too many reusable screens, then digital is the way to go. So again, everything that we do is very bespoke. It's on a project by project basis. So talk to us, and we'll provide you with the costs and the benefits for both options.
We do actually have another question in about adhesives, so apologies for this. Are all adhesives fire resistant and safe for use on higher risk buildings, or do you have a range of adhesives for lower rise buildings as well?
We only use one type of adhesive, and that adhesive in its own right, wouldn't be suitable for a high-rise building. When it's combined into the composite panel, which is what's tested, the EN 13501-1 test that is done, the fire classification, and that all of the tests that go into building that classification, the product is safe for above, what's coming up is 11 meters, 18 meters currently, but next year it will be 11 meters through all the nations of the UK. So we don't use a different adhesive for low rise. No. It's the same adhesive and the same fire performance with every panel that we manufacture.
And I should say that, fire resistance is obviously an issue that's very much on everybody's mind. We are going to come on to that in a bit more detail in part 2, so we will be coming back to that. Jason, what else is piquing people's curiosity?
Sure. I've actually got a question in which will go back to what you talked about with screen printing, and it's also related to the aesthetics. How can you incorporate signage in the glass panels?
There's different. No, there are different ways that you can incorporate signage. The first is obviously to have the signage actually back printed onto the glass, either digitally or screen printing, and then it's baked on. The alternative way, and if you go to perhaps Manchester Airport, you'll see examples of how it's been done there, where what we've done is we've cut out of the glass in the factory the shape of a sign, and then the designers of the airport have been able to slot in exactly acrylic signage that sort of suggests, arrivals this way, toilets that way, and then backlit them. So as long as we work closely with the designers to incorporate that sort of signage, we can create the cutouts that will do that. We're doing underground stations currently where they have what they call ades signage, which has to be cut out specifically and mounted in certain spaces. Different ways that signage can be done, back printing or cutouts, either or. They're both possible with Sto Ventec glass.
And I think it's worth saying we are going to look at some case studies at the end of the webinar. So we will see some examples of some of the things that both Darren and Greg are talking about, which I think will really help to put it in context. Jason, what else is hot on people's radar?
Well, we've got one audience member who is curious about the heat soaking process, and I was wondering if they could elaborate on what that is and how it works.
Toughened glass in particular, it gets what's known as can get little inclusions in it when the glass is being manufactured and when it's being toughened. And what that can result in is that the first time the glass after manufacture is heated up. So for example, let's say could be potentially installed on a facade. And the first time it gets some strong sunlight on it, that inclusion expands very rapidly and shatters the glass, which obviously no one really wants to see. So what happens is, what we do with the heat soak test is that every panel that is manufactured then goes into a heat soak is heated up effectively for a number of hours to ensure that any inclusions or any glass panels that are likely to break within the factory and are then replaced rather than being delivered to site and breaking when they're installed. So typically you can also see this happen quite a lot with things like oven doors, glass pan lids. Quite often you can get your nice new oven, install it, and you'll find that the door collapses, or sometimes actually can even slightly explode when it's heated up for the first time. So we ensure that the likelihood of this is incredibly small by doing a heat soak test with every panel that we manufacture, and that's standard. We don't way back when we first started with glass back in the 90s, that wasn't a standard process. It was something that had to be requested, but we've since learnt from that, and every single panel that goes through now is heat soak tested. And I think it, from memory, might be wrong here, but I think it reduces the chance of something like that happening to about 1 in 40,000.
We've also got a question regarding carbon cost, and they ask, what is the estimated embodied carbon per square meter of Rainscreen build-up?
Okay, yeah, I'm surprised it didn't come up earlier. Darren, do you want to tackle that one?
Oh, I'm not sure I can. If I'm honest, I know that we have EPDs, environmental product declarations for Sto Ventec glass. Off the top of my head, I'm afraid I couldn't give you that answer, but happy to forward a data sheet or an EPD to anyone. Greg, perhaps you can elaborate.
Obviously, that would vary probably quite significantly with the build-up of the wall. So it would vary with the amount of thickness of insulation that you're putting in onto the facade. But like Darren says, I think if we can take a note of that person's contact details, then we can come back on that. I am aware that an EPD is in progress right now as we speak, probably likely due towards the end of this year, but we've likely got a figure for that already. available, so we could provide that at the end of the presentation.
I think that would be really useful. I think, all issues really relating to environmental performance, obviously increasingly everybody's aware of it and clients are expecting it. So if people have specific questions relating to sustainability, is there a kind of particular person at Sto that they should go to, or is it you two that will field queries on that? Darren, what would you say to that?
Yeah. If you come to us in the first instance, but I also should mention that Sto is obviously an ISO 14001 compliant company, and that's not just the UK, that's globally. And at the head of that organisation is a gentleman by the name of Dr. Ika Mesov, and he's our environmental specialist. So that's all he does all day long, 24. Well, not 24/7. I'm sure he stops at 5 or 6 o'clock like the rest of us. But that's his sole purpose is EPDs, measuring carbon footprints, embodied carbon, cradle to grave. Just the whole that's what he does, and he has a team of people who work for him. So it's something that Sto takes incredibly seriously. We have our own zero carbon targets as a global business that we're working very much towards. So it's something we do take incredibly seriously. So anything like that, send it to myself or Greg in the first instance, and we'll engage directly with our colleagues in Germany to expedite some responses for that.
We've got a question which is more of a general query about systems build-ups. I was wondering if they could expand a bit more on that area if possible.
Darren, that's probably your turf, isn't it? It's quite a broad question, but can you expand on systems build-up?
Yeah, absolutely. I mean, system build-up is, obviously, as a Rainscreen system or as an insulated Rainscreen system, the primary element is the insulation. Everything else is sort of icing on the cake and subconstruction. So it's achieving whichever U value target that you're looking to achieve. So, let us know what sort of thermal targets that you have. Let us know what the actual structural wall build-up is. So the internal skins, how thick is the plaster or plasterboard on the internal skin, how much lightweight steel frame and insulation is in the stud, what sort of sheathing board is on the outside, that full build-up. And then we can then go and calculate a U value and say, right, you need 100 mil, 150 mil, 200 mil of insulation. So once the amount of insulation is established, then we can look at the subconstruction. And the build-up of our system, once it goes on there, is initially the stainless steel brackets go onto the wall. And I think the second part of the presentation will talk more about why we use stainless steel brackets. Once those are fixed onto the wall, you cut slots into the insulation and slide them over the top of the stainless steel brackets. So there's no gaps. It's just a straight cut. Once the insulation is on, you can then put an aluminium T-profile that slots into the stainless steel brackets. An aluminium graph horizontal rail goes across the back of that and is mechanically fixed to that. And all of that is done on site. Meanwhile, glass composite panel is being manufactured in the factory. That arrives on site complete with the backing rail on it, and that gets hung and adjusted on site. So it's a process, and hopefully the second part of the presentation will cover a little bit more of that in a bit more detail.
We talked about adhesives, but this one actually wants to know a little bit more about the backer panel and also the fusing of the colour to the rear face of the glass. Want to know more about how that is done and what possibilities are available, possible rather.
Okay, Greg, can you tell us a bit more about that, please?
Yeah, so the backer panel itself is made from perlite, which is manufactured in turn pretty much by melting rock. It's a sort of material that's been around for a long time. So that's then the perlite that's manufactured is then has a small amount of epoxy binder added to it and is formed into the backer panel. So this makes the backer panel particularly inert, so it doesn't, under influences of cold or heat, it doesn't expand or shrink, and it's also particularly resistant to any moisture influences. So that gives us a good solid basis to bond the panel to. The glass panel itself, the colours are we use typically we'll go off a RAL color chart. So that's typically our main basis for color, and the pigments then that are used by the process. I mean, by virtue of the process, the manufacturing process, where the pigments are fused into the back of the panel, back of the glass panel during the manufacturing. That's happens in the kiln, the glass kiln, when the toughening process is underway. So those are mineralic pigments. It's quite important to distinguish between mineralic and organic pigments. Typically, organic pigments you'll find in paints, renders and things like that, or in plastics even also. And these are the sorts of pigments that typically in sunlight or intense UV, they'll start to fade over time. Mineralic pigments don't do that. Mineralic pigments are particularly stable, so they've got a very high UV resistance, and they won't typically you won't see, you'll be able to distinguish color fade over time, even under the strongest influences of sunlight. So the color choices are wide, very broad indeed. We can also, within certain limits, we can also match colors. So if someone has a certain color that they want to use, which isn't, for example, isn't within the RAL color chart, then we can see if we can match that. Quite often we can. Using mineralic pigments, however, does have one slight downside, in that the range of color typically isn't the same as you would get with an organic pigment, so with a paint. So whilst we have probably several hundred RAL colors available to us, there is some limitations, particularly I think around, from memory, I think around sort of purples and violets for some reason can be tricky. But outside of that, we can usually get there or thereabouts to pretty much any requirement.
Not sure how quick this will be, but I think it's pretty important. It's about the installation process. Are there any kind of bespoke sub-construction requirements, particularly with regards to thermal performance, such as insulation thickness? How does that relation, the relation of that into sub-construction details? They're wondering if any details that were required for that.
Darren, I'm going to put that one to you. Sorry, that
Sure.
probably doesn't
Okay.
lend itself to a succinct answer, but...
No. Okay, so our standard details and drawings, you'll see that insulation can be whatever thickness is required. Our bracket lengths go up to 360 mil off the shelf, and we can do larger sizes up to, in the region of 600, I think is the largest we've done. So it's more a case of what sort of size insulation is required to suit your thermal target. Now, I think we're going to cover this more in depth in the second part of the presentation, so I won't sort of do the whole spoiler alert thing. But we've sort of checked and tested and double tested the concept of using aluminium and stainless steel components in order to maximize the thermal performance, but at the same time maximizing the strength of the system, while trying to sort of keep control of the commercial aspects. So you'll find in the second half of the presentation there's a lot more detail that will answer the question.
Okay, thank you very much, both of you. Now we are going to move on to the next presentation, which is going to go into a bit more detail, as Darren said, about performance and compliance. So now part 2.
Welcome to part 2 of this Sto CPD video. In part 1, we covered glass Rainscreen principles and design options, and now in part 2, we'll explore performance, including moisture protection, wind loads, impact and blast performance, and fire safety. Let's discuss building physics and look at the way that the glass Rainscreen system manages moisture. The insulation can eliminate cold bridges if the correct components are used. The use of stainless steel brackets can vastly reduce or even eliminate cold bridges. Internal building moisture drawn into the cavity under a natural pressure differential leads to a reduction or elimination of internal damp and mold. The walls can breathe, and ventilation ensures quick dispersion of water vapor. The insulation covering the substrate also helps to maintain a stable year-round internal temperature, which keeps the wall dry and reduces movement. When we consider the thermal performance of this type of external wall insulation system, The benefits of using Rainscreen construction are: stainless steel performs far better in its thermal performance and is best used as the supporting brackets. Although the material is more expensive than aluminium, it is far stronger, meaning fewer brackets are required, making the overall cost comparable whilst minimizing thermal bridging. Almost limitless U-values and insulation thicknesses are possible, with brackets available up to 600 mm as standard. Longer brackets can also be made to order. Insulation thickness is only limited by availability of fixing dowels. Aluminium is an excellent material due to its high strength-to-weight ratio and comparative low cost, and is therefore most suitable for use as supporting profiles. Let's look at the sub-construction format. In A, the minimum possible configuration for a 3-meter length of T profile is shown with a single fixed point and 2 gliding point brackets. B shows that additional fixed point brackets may be necessary to carry the weight of the system in some cases, for example on lower strength substrates such as brickwork or light steel frames. Depending on wind loads, substrate properties and system depth, more brackets may be required. With recent changes in building regulations, it's important to verify the chosen system is suitable for use in the intended application. If we examine fire as one such regulation, the following is important. Insulation and cladding panels over 18 meters in height must be of limited combustibility. This is in accordance with the ban on combustible cladding, which came into effect on the 21st of December 2018 for buildings in England and Wales. Cladding specified on a multi-storey building must not appreciably accelerate the rate at which fire will spread up the building. Fire breaks must be designed to work in conjunction with a particular building construction and cladding system. They must provide a barrier to fire and close the cavity in a fire event. Seek the approval of the fire officer and building control officer for all matters concerning fire break design and strategy. A typical section detail showing a fire break rail is shown here. Fire barriers may be required to limit the spread of fire within a cavity. They form part of the overall fire strategy for the building and are part of the designer's role. For ventilated Rainscreen cladding, the barriers may consist of horizontal open state barriers at floor levels, vertical full-fill barriers at party walls, full-fill fire barriers around openings. Fire barrier manufacturers can act as a good source of advice. Wind load is often the largest force applied to a facade, and its values vary with the size, shape and location of the building. Corners of buildings attract the highest wind loads and are commonly known as rim zones. Although wind acts in both positive and negative pressure, normally negative suction effects are most important. The number of fixings are directly related to the wind load calculations and the substrate pull-out capacity. Note that on metal-framed, sheathed substrates, the fixings will need to go into the metalwork. It is highly unlikely the sheathing board will be able to carry the dead load or adequately resist the wind load. When specifying a glass surface, it's important to know the performance of the system in relation to its finished location, as no significant portion of the cladding should detach and fall when subject to certain levels of impact. For example, public safety zones require rigorous impact and blast testing. CWCT TN 76 gives good guidance for testing regimes. Let's see some of the different types of test available for impact and explosion forces. Sto Ltd Glass A has BBA certification and a reaction to fire classification of A2. It's also undergone extensive bomb blast tests with equally impressive results, making it the safest and most robust Rainscreen cladding system available. Each country and sector has one or more departments responsible for the protective security of critical assets. For example, critical national infrastructure, government buildings, embassies, and commercial property. SIDOS, security in the design of stations, and ASIAD, aviation security in airport development are part of a safety program implemented and administered by the Department of Transport, DOT, and CPNI, the Centre for the Protection of National Infrastructure. Strict guidelines are mandatory and should be followed in the design and material specification processes. In terms of glass cladding, the guidelines cover many different subjects, such as the structural integrity of the overall system, the strength of individual system components, and their behavior in an explosion scenario, especially their ability to minimize any risk from flying debris. Here's a selection of reference projects. The new Paddington Station in London, and the other in the new T2 extension at Manchester Airport. More UK projects for Sto Ltd glass installed at Moorgate Station, Taplow Station and Reading Station. The glass can be installed externally, internally, as wall cladding or to surround lift shafts. UK projects demonstrating the reflective mirror effect finish, how signage can be incorporated into the Sto Ltd glass panels, and another example of the glass being used internally at a research and development centre. Some of the diverse and large international projects in Europe. We have many Sto Ltd glass Rainscreen cladding system project references around Europe, all showing a wide variety of designs, finishes and good use of the large colour range of glass panels that you can choose from. The BBA will test all aspects of a UK Rainscreen cladding system against all relevant criteria and design considerations. In general, bodies such as the NHBC will not recommend a system without a BBA. Typically, the BBA applies to the whole system and can be applied to new build and refurbishment projects. The BBA certification provides fit-for-use confirmation, providing it is installed, used and maintained as set out in the certificate. Most certificates provide an expected service life in excess of 30 years. The BBA also ensures the system complies with relevant building standards. Glass is not only an attractive material, it's also weather-resistant, long-lasting and 100% recyclable. The carrier board the glass is bonded to is manufactured from perlite, a natural ore. Sto's manufacturing plant in Weizen, Germany is 100% climate neutral. Glass is easy to clean and requires very little maintenance, with standard glass cleaners being recommended as you would use for normal glass. The composite glass panels are designed and manufactured to remain safe under circumstances where they may become damaged. Any damage results in the glass face of the panel shattering. The small glass fragments will remain bonded to the backing board, avoiding risk from flying debris. Due to the intrinsic nature of a damaged panel, it can remain in place until a replacement panel is ready for installation. Glass Rainscreen systems are simple and fast to install when using brackets and profiles, even when levelling undulations in the substrate. They provide optimal thermal insulation and moisture control and are tested to the extreme in relation to fire, impact and blasts. No wet trades are required during installation, so there's no need to consider drying time, weather conditions or waste materials on site. The systems are generally bespoke to the project and there are many design options available: colours, surfaces, textures. Tough and built to last, glass panels are designed and manufactured to remain safe. The finished panels can be easily cleaned and replaced if they are damaged. The non-combustible mineral fibre insulation also acts as acoustic insulation to prevent the transfer of noise along the insulated facade. Thank you for watching.
And now we're going to have another run through some questions that are coming in from viewers. Once we've done a Q&A with the panel, we're going to do some case studies at the end. But first of all, Jason, what have people been asking about?
So a few questions on fire, which is to be expected. The first is, how do glass rain screens perform in the event of a fire?
Greg, I'm going to go to you. You obviously touched on this in part one, but do you want to expand a bit now, please?
Yeah, so Sto Ventec glass A has been tested to EN 13501, which is the standard which is required by the building regulations for most buildings above 11 meters in all parts of the UK. So that means it's essentially, according to the building regs, it's of limited combustibility. So when a fire is when it's subjected to a fire, it has a very good reaction, or actually no reaction. Very little reaction. Very little smoke is generated. The material itself doesn't contribute to the spread of flame across the building surface in any way, appreciably in any way. What's particularly good to note about Sto Ventec Glass A2 is that we did this test on the front face, but also on the rear face as well, which is the face which is into the cavity, which is also possibly, if a fire takes place, that's where a fire is going to propagate, as you can get, or typically you will get a chimney effect in a ventilated rain screen. So it's quite important that in that cavity you have as little flammable material as possible. So we're pretty safe and secure that the panel itself is not going to ignite in any way, whether the fire's on the outside or the inside of the cavity.
I think there's one specific question which I'd like to ask, which has come in actually from someone else, and it's regarding the open fire barrier. What is the minimum gap required for open state fire barriers? Is there a minimum that is required?
Typically, the minimum will come from the NHBC, which will be 20 mil. That's a 20 mil open gap, and an open state cavity barrier, which we're not actually responsible for these barriers. They're manufactured by other companies. But the open state cavity barrier, typically it's an intumescent material on the face of that cavity barrier, which then reacts to heat. So when the heat reaches a certain level on the face of that intumescent material, it starts to expand, it reacts, it expands, closes off the cavity. So typically these open state cavity barriers will be specified for a maximum distance that they can close off for the time that's required. So you'll probably be looking at, I think the minimum is, I think it's 30 minutes. And most of these cavity barriers will perform for up to 2 hours. You should be able to get that off an open state cavity barrier. So that intumescent material expands, blocks off the cavity, if you like, so the fire cannot get past it. It also stops any smoke going up through the cavity as well. So yeah, that's how they perform. But as I said, the cavity barrier design is usually part of the overall fire strategy for the building, so it incorporates all sorts of other elements as well, sprinklers and all sorts of other stuff as well. And that's a sort of a holistic design, which is carried out by the architect, usually in combination with some sort of specialist engineer that would look at that. And also the cavity barrier manufacturers themselves can also usually assist. As you could appreciate, they're specialists in that area. They can usually assist designers with any kind of design for a ventilated rain screen or any other kind of facade for that matter.
Got a question that's related to regulations. How do these glass panels measure up to building regulations and meet current standards?
Okay, quite a broad question. Darren, I'm going to put that to you. What can you tell us about compliance with regs?
I mean, the system has obviously been tested multiple times for all different aspects, whether it's impact, bomb blast, fire, CWCT. There's a number of things that have taken place with the system, and ultimately they're all sort of brought together one sort of certification in the BBA. So we've got a BBA for the system, which breaks down its levels of compliance to all the UK regulations, meeting wind load requirements, fire requirements, implements, all of the above. But the BBA, I think, is probably the go-to document summarises all of those elements. It's a custom, and they're the highest certified, most compliant system of its type in the.
Yeah, so as Darren sort of as Darren explained there was we have this the BBA certificate is a good way to look at how the system can contribute to satisfying the regulations. So typically it's Part A. So particularly Part A is primarily where Rainscreen is concerned. It's to do with the wind load and it's supporting its self weight. It's dead load, and then Part B is then to do with fire, as we've just discussed. So it's to do with around cavities and also the reaction to fire, contributing, restricting the external fire spread on the face of the building. And then finally, you've got Part C, which is concerned with resistance to the passage of rainwater. So whilst this type of system, any open jointed system, is not watertight and it's not airtight. It's got a lot of open gaps around it. It does contribute to the passage of rainwater onto the inner surface. So your water tightness and air tightness is provided by the substrate, which typically today would be a sheathing board of some kind. That's mostly what we come up against. It's a sheathing board on the steel frame. So that part of the structure would need to perform in that respect.
So it's interesting you talked about kind of moisture there, because there's a question regarding, again, it's relatively general, and it's what are the chief moisture control challenges when integrating a glass Rainscreen facade into one's design?
Certainly. So what we will do as part of working together with a designer is we'll perform the U-value calculation that also contains a condensation analysis. So we'll ensure that we're not going to get any condensation in the wall anywhere. Rainscreens are particularly good at dealing with moisture from the inside. So if you have a breathable wall, any moisture that comes through is taken away rapidly by the ventilated part of the ventilated Rainscreen, so that air gap that you've got on the outside. But also typically, particularly with steel framed structures, if you've got a light steel frame that you're putting a sheathing board onto, these can be particularly tricky when it comes to condensation. So quite often we would recommend, if it comes up in our condensation analysis, we'd recommend the incorporation of a vapor control layer, probably in the inner surface somewhere in the inner leaf. Normally behind plasterboard or some kind of internal finish, you'd have some kind of vapor control layer. But we'll do that together with the designer, and we'll do the analysis first and see where we get to, and then if we think that it's required, we'll recommend that a vapor control layer goes in.
When choosing a colour for the glass, how light does it have to be before colourless glass is specified, and how does this affect the price?
Interesting one. If I'm honest, in my time at Sto, I've only sort of dealt with RAL colours. When your questioner asks about colourless glass, or are they talking about clear glass? Because the concept of clear glass doesn't necessarily work with a composite panel. If you were to have clear glass on the front, your 6mm or 8mm of glass, you would then be able to see the adhesive backer behind it, and in turn the obviously the rail and the fixing that comes through the back of the board. It's designed to be an opaque system. So when your questioner asks about colourless glass, we would still put a white on the back of that, so it remains a neutral colour, but it would not be clear, obviously, because of the adhesive. With that glass, again, if it's going to be a white or a light colour to give the impression of being clear, we'd always recommend that you go with something that's been engineered to be a low iron type of glass. In the first part of the presentation, we touched on the greenish hue that sort of comes as a natural byproduct of the iron content within glass. So by going with a low iron type of glass, it gives you a much truer colour. So if it's a white, you get a bright white as opposed to a greenish off-white, which is the standard.
Sorry, I'd just maybe add with the low iron glass, typically you would use it on, as Darren said, lighter colours, whites or pastels, lighter pastels. By the time you're sort of getting into the heavier colours, the more intense colour shades, that sort of greenish hue tends to disappear, or it can't be distinguished anymore. So you wouldn't need to do that.
Okay, thank you both. Jason, was there something in that question about costs that we didn't get to?
Yes, quite right as well. They're asking about how, essentially, how they asked how light does it have to be before colourless glass is specified, and how does that affect the price? You alluded to colourless glass, but I was wondering if you could allude to, well, they were wondering if you could allude to how the colour of the glass affects the price.
Well, Darren, is that how long is a piece of string, or is there? Is there a rough guide?
It is, if I'm honest. Yeah, it is, if I'm honest. I mean, with everything commercial, it is very much how long is a piece of string. It's not necessarily the colour that adds the most impact onto the price of the glass. It's actually the size. It's actually the amount of cutouts. It's actually the edge detailing. It's once the wind load is calculated, do we need extra rails on the back? The colour has a very, very minimal bearing on the overall price of the system.
What level of impact can the glass panels withstand?
So with CWCT 76, obviously it talks about impact hard body, soft body testing. Greg will be able to go into the details of that, but we have a YouTube video that actually shows all of the testing that took place with hard body, soft body, cranes swinging things at glass panels at a test centre, and you'll see that the glass remains bonded to the back of panel under impact. So there's no danger of flying glass fragments, splinters coming away from that. So secondary to that, aside from the impact, is obviously the bomb blast. I think for those of you who've ever been close to an explosion or an IED or of anything of that nature, you're aware that you've got two different things that are happening there. The first is obviously the shrapnel that's coming away from the bomb, and the shock wave or the blast pressure that comes away from it when that explodes. And then secondary to that is obviously the fragmentation of everything around it that creates flying splinters and shards that cause a tremendous hazard to the public. So as part of the impact testing, the impact of that blast wave has been tested. We took our glass panels up to the Lake District. We took a couple of hundred kilograms of TNT with us, and then we blew our panels up. We did these to specified standards, so a 10 kilogram rucksack bomb or IED from 6 meters, 100 kilogram rucksack bomb or PBIED at 25 meters and 15 meters, and the idea was to prove that there was no flying shrapnel, and we passed all those tests. Greg will be able to expand on the impact and the actual standards they all achieve, but the end result for us is to have ASIAD compliance, CIDOS compliance, protection of national infrastructure. To be compliant with those standards for us it's a real bonus.
Okay, so Greg, can you expand on that a bit for us, please?
Yeah, so impact is tested in line with a guideline produced by the Centre for Windows and Cladding Technology, also known as CWCT. So that's in Technical Notes 75, 76. And that defines a range of tests with different impactors into the glass at different levels of energy. So you've basically got hard impact, which is simulating a stone or a sharp object being thrown or projected into the glass. And you have a soft impact, which is potentially someone, it could be a body, someone stumbling, falling into the glass, or on a high building, something like a cradle being used for cleaning, which then swings and impacts into the glass. So these have a variety of levels of impact, from relatively minor to actually pretty high. So you're swinging something like I think it's a 50 kilo medicine ball at its highest. That's probably the highest one is the soft impact. Funnily enough, it's a 50 kilo medicine ball being swung from I think it's about 1.2 meters away at an angle of starts at an angle of 90 degrees, and so swings down into the glass itself. And what's being measured there is the damage that occurs when those impactors hit the glass, whether it damages the panel or not, but also more fundamentally whether any parts fall off and could therefore cause harm to anyone down below. So typically it's seen that panels can break, particularly glass panels. They're allowed to break, but they must remain in place or have minimal loss of material off the surface, and so that's what those tests prove. With blast, the actual requirements of the blast test are still confidential. Still, it's a secret. We don't even know what they are. You basically get a rating from the blast test. So you're looking at again typically the amount of spall. It's known as spall, the amount of material that comes away from the glass panel and then scatters as a due by virtue of the sort of suction of the blast. So a blast wave goes out, creates a pressure wave which hits the panel, but then you get air rushing in to fill that vacuum that's created, and then you get a lot of suction on the panel system itself, and that's when damage can occur. You get quite a lot of collateral damage through flying fragments, splinters, and that's what we're trying to prove, or what we do prove when we do the blast tests, that within certain limits, a limited amount of glass comes off the panel, so that additional casualties, additional damage is minimal from that panel.
Okay, thank you for that. Jason, what other subjects are coming up?
Yes, we've got quite a long one about the substrate requirements and the brackets, and we're going to split it into two to make it a bit easier. So do bear with me. Do the brackets themselves contribute to the creation of a thermal bridge? And if not, how?
Darren, are you able to answer that for us?
Yeah, to a certain extent, the use of stainless steel obviously minimises the thermal bridge. That's I think we had a slide that sort of demonstrated the use of, if you were to use aluminium bracketry, and the amount of insulation that you would need in order to achieve your U value, and then using stainless steel. So thermally, it's a far more stable and more efficient material. In terms of bridging, there is an element of bridging, but it's certainly negated by the insulation and the rest of the system.
Okay, great. And Jason, what was the second part of that question then?
Sure. So are there any specific substrate requirements, and how many brackets per meter is it recommended that is used for the Rainscreen cladding?
Greg, are you able to answer that? It's a very specific question.
Yeah. I mean, there are requirements regarding the pull-out of the fixings into the substrate, and that will vary significantly with the type of substrate. But I would add we can pretty much accommodate pretty much any kind of substrate that you could come across. So we'll work with the designer to achieve the correct fixing for the substrate. So we have a variety of fixings at our disposal. Sorry, what was the second part of the question? I've lost my thread.
How many are stipulated to be required per meter, or is that wholly dependent on substrate itself and
that's
and
wholly
the design
dependent
of the green?
That's wholly dependent on the substrate. Also the wind load that's anticipated. So we actually have a calculating tool which we've had developed by a firm of consulting engineers, which enables us to provide pretty good guidance as to how many brackets are required per square meter. Typically, you're looking at something like 2.5, 3 brackets per square meter in most cases.
At the end of life of the cladding or building, how are the panels, including glass, adhesive, and perlite, separated and recycled?
Greg, do you know the answer to that?
That's a good question. We're not quite there yet with that.
Okay, that's work in progress.
That will be part of our CPD. Currently, it's very, very difficult to do. If you've ever come across something like a Pringles can or something like that, which is made of different materials, it's quite difficult. In fact, I think they are still pretty much unrecyclable, and so would not be recycled. So at the moment we're still in that sort of situation, but we are working towards ways in which we can recycle all of our systems. Currently, we're looking at EWI, because that is typically they have EWI has a far higher square meterage of installation around the UK and also Europe. The glass rain screen is a very small, by proportion, is proportionally very small. So it is something that we're looking at, and it will be obviously subject to the EPD that we produce, or is under production at the moment, and will come out towards the end of this year.
Thank you both very much. I think now we'll move to look at some case studies. And we've selected these, or rather Sto have selected these, really to show the kind of breadth and range of applications and some of the issues come up. We're starting off with two examples that are demonstrating the use of rain screen facades in smaller domestic properties, which tends to get overlooked. So we have here Davenport House, and I think I'm right in saying this is in the USA, and then this house is in Austria. So, Darren, is there anything you want to say about the particular challenges of these kind of smaller projects?
Yeah, absolutely. And it's not so much actually the challenges that are faced with these, Isabel. It's more a case of the fact that I think with the level of certification and impact testing, and we're talking about bomb blast and fire and over 18 meters, and like you say, buildings like this often get forgotten, and people tend to think, oh yeah, glass is only an option for big office blocks and hotels and airports, etc., etc., etc. And we found that during the COVID crisis, as office projects got shelved, as hotel projects got shelved, as airport expansion was put on hold until the tourism industry took off, we thought that we would see a significant drop off on our Sto Ventec glass projects. But interestingly, we had a sort of flood of domestic opportunities come through, where people are looking to just do something different. And currently, I would say that of the projects that we've got on our pipeline at the moment, at least half a dozen, maybe more, domestic properties where people are looking to upgrade and do something different, do something challenging. So if there's anything that I can say to your audience today, is it's not just the product and system that's designed for high end big projects. It's something for everyone.
And Darren, on these smaller domestic projects, do you think it's the client that's driving the interest in glazed facades, or do you think it's the architect?
I think initially it's architect driven, in the sense that there's some frustration from their perspective that projects that they're working on during COVID have yet to sort of come back out post pandemic as yet, and so it's an opportunity for them to express and let their creativity have an outlet. So yeah, okay, we can't do it on the Premier Inn, so to speak, so let's do it here on Mrs. Jones's house. So yes, from that one direction, but also from the opposite direction, as people, clients and homeowners look around at the larger commercial projects, especially if they're looking at building their own home. They've bought some land, they want to do something with it. They draw their inspiration not just from architectural magazines, but also bigger and larger projects that they want to incorporate into their own personal. So yeah, it's a little bit of both. It's a little bit of both, architecturally driven and client driven. We're just happy to assist.
Okay, great. Now, our next case study at the other end of the spectrum, Manchester Airport Terminal 2 extension. Greg, I'll go to you. Talk us through some of the issues here.
Yeah, so what Manchester were after with this, this is on the land side, check-in side of the airport. Obviously, you have sort of competing, in many ways, competing requirements. So you have a requirement for public safety. We've talked about bomb blast and impact, but you also have a requirement for a high level of finish, a very sort of high level of aesthetic, particularly in this area of the airport, which is used by a lot of people, where a certain impression needs to be made when people are jetting off on their holidays or their business trips. So we had the black glass was used on the part that you can see there, where you go through into the security, and also there are two lift towers at the front of the at the front of the building. So we had those two competing competing requirements in many ways, because quite often to make something safe in the event of an explosion or a fire or impact, you are looking at quite tough materials. So you're looking at metal, maybe concrete, something like that. So we were able to use the glass, and also we were also able to incorporate the signage that Manchester were after as well. So here you've got the signage on the side of that part of the building showing the elevators, which was I think this part was back printed. But we also have other signage in other areas where the glass was actually cut out to receive an acrylic sign into it, which was backlit. And there are other areas where we've actually just effectively had holes drilled or formed the glass with holes in, so that support brackets for suspended signage can come off, and that you can also get the power cable through that through those openings that we've made to also backlight those parts as well. So it was quite that was quite a challenge. We also did this project in combination with a company that manufacture a wall liner, which isn't glass. It's a sort of looks like a matte painted wall effectively, and we worked very hand in hand really with this company to incorporate the two systems side by side, so that they're pretty much seamless when you're in the airport, and you get very good, very clean junctions between the two systems.
Okay, great, thank you. So Greg, I'm going to ask you to talk about the next case study as well. We've got two images of this museum in Norway, and I particularly like you to about the relationship between the lighting design and the glass facade. I think if we go to the next, yes, so you can see a completely different appearance by day and by night. So how did you set about achieving that?
Well, the architect wanted to achieve this difference, if you like, to make the building appear significantly different between the two times of day, between the darkness and the light. And also we were able to achieve this by sort of playing with the grid. So the architect looked at the sort of light design that they want, and then we looked. If you just flick back, you can see the joints actually between the glass panels themselves. So whilst the building itself looks quite triangular and the shapes are almost quite random, or appear quite random, you have quite consistent horizontal lines between all of the different levels of the building, and this makes it easier for us to manufacture the panels to fit, but also incorporate these lighting strips that the architect wanted in their design. So we were able to fulfill the technical requirements, but also happily we were also able to design it so that the architect's aesthetic could shine through as well. So yeah, quite a challenge, but really good result.
Darren, I'm going to ask you to talk about this next project. So this is the Premier Inn at Archway in London, and very clearly the business of getting colour into the glazing is absolutely fundamental to this. So how much was that you? How much was that design team? And how did you actually achieve this result?
Well, I think the primary driver behind this was the fact that when you're going to build something that tall in a central location that's residential, it doesn't become an absolute eyesore to everyone who's established living in the area. So the primary driver was they wanted something that at any given time would match the colour and shade of the London skyline. So you can see there, I think there's 6 different shades of blue that sort of gradually enter into grey, and it was a case of identifying the colours, the RALs, the samples, providing those, getting individual sign-off on the samples, and then working with the architect to understand the sort of graduation of those colours as they decrease and at what frequency. And so it was an interesting project to deliver. And considering that this one was done a number of years ago, Greg and myself had occasion to be there only a couple of weeks ago, and it still looks still looks fantastic. And when you look at it in comparison to the sky behind, there is always at least one section of the wall that sort of blends with the background. It's certainly not an eyesore on the London skyline. It adds to it.
Okay, brilliant. We're running out of time, so I think I'll just skip through the next two slides quickly, which are just to show examples of internal applications. We've got the Science and Innovation Centre in Hull and the University of Birmingham. But Darren, I'll stick with you. And what I would like you to do is talk a bit about the next project, which is Wolverhampton Girls High School. And I think similar issues here, really, in the kind of attention to the aesthetics of that facade.
The architect wanted to achieve a very, very specific and striking facade type. They actually wanted a mirrored type of glass. We responded back to them that using our black standard float glass as a gloss system would provide exactly the aesthetic they were looking for. So we were able to advise them on that, and the end result really is quite striking.
Greg, can you talk to us about this one, which is a project I think everybody will know? So Paddington Station. What were the challenges? We've got a couple of slides of it.
Well, again, yes, we've got the public safety zone aspect of it. So it needs to have all the public safety zone requirements that I talked about previously with Manchester, but also the architect wanted to reflect the design of the sort of circular design, which is part of the original design of the station back in I guess it was the 19th century when the ironwork first went up. So this shape is reflected throughout the whole of the station already, and it's brought into this facade, this part here. This is the entrance to the new entrance to the Elizabeth line. It's brought into this part of the facade here with back printed glass. So we did this with the screen print. It's really suited to screen print, this pattern, because it's repeated all over the whole facade. So it starts off with these small circles and graduates then into, as you sort of look at the pattern, you see it repeating and repeating into larger and larger circles that sort of intersect and create these sort of diamond star shapes as well. So those were the particular challenges. Also the actual jointing itself, the applicator had to be really careful when they were doing all of the set out, because the joints were quite narrow, and narrow joints really show up if you get the panel out of line. That misalignment really shows up with narrow joints far more than with wider joints. So there was some very precise setting out needed to be done here, and I think pretty much it's been a really good result.
Jason, do we have one last question? So anything that's coming in again and again from the audience?
You did allude to it earlier, but people were asking if there are any specifics regarding wind load calculations and the process involving that.
Darren.
Yeah, absolutely. Obviously, it's a major concern. You've got wind loads that are acting on a facade surface, but more importantly, you get the negative suction that occurs at rim zones. And when you have instances of that, then it's possible that the wind load can remove a facade system from a wall. So it's absolutely critical that we work early with the architect to understand the forces and the dynamics that are acting on the building. We will either engage with the appointed engineers to obtain a wind load calculation report, following which, as Greg alluded to, we'll process that through our own sub-construction calculator in order to define the centres, the brackets, the spacing, the quantities, in order to make sure that system stays on the wall wherever it may be. So in coastal climates where you've got high wind loads, where you've got tunnel effects in central London, those sort of places, very, very important. And it's something that we work closely with the architect to achieve.
Okay, brilliant. Thank you very much. I think we'll end it there. Just to reiterate, if you have a question and we didn't get around to answering it, please do email it. We will get back to you, or rather, Greg and Darren will get back to you. Everybody who registered is going to be sent a recording of this webinar, so you can watch it at your leisure. Please share it with your friends and colleagues, and please do send questions. Now I'd like to wrap it up. So huge thank you to our programme partners Sto, and especially of course to Darren Greenwell and Greg Astle. Thank you to Jason, and thank you all very much for joining us.